Lesson 1.4, we're going to be working with absolute values. This is a really important lesson in that absolute values come up a lot in the calculus courses. I'll just remind you some of the things we did in the last two lessons. We talked about piecewise defined functions. We also talked about function composition, and both of these will come up today. So I'll start with an exercise really from the last lesson, which is function composition. And this comes from our textbook. We're given f of x is absolute value of x. G of x is 5x plus 1. Let's just compose in each direction. So if we first calculate f of g of x, well, we put in g of x everywhere we see an x. And so it's this function, the absolute value of 5x plus 1. But if we go in the other direction, it's a different function. Here we put in absolute value of x for x in the expression for g. We get 5 absolute value of x plus 1. Okay, that was a nice recollection somewhat of some things we did last lesson. But the question is, what is this function? Certainly we can compose in each direction, but our goal today is to further understand and work with the absolute value. Well, the answer, you can see it here. You can, on one hand, define it as the square root of x squared, but on the other hand, and this is a very beneficial way to think about it, absolute value of x is really a piecewise defined function, and you can see it here for non-negative x. It gives you x, and then if x is negative, absolute value of x is minus x. But note that absolute value of x is always non-negative. Now, immediately we can write down the domain, minus infinity to infinity. We can also write down the range, so you can see it from the graph, right? If we push the graph toward the y-axis and see what it traces out, we get 0 to infinity. This is the range of this function. Let's just do some examples evaluating. Now here you see we have some absolute values, and we have some composition, and we have a sum, but this is a wonderful function to practice evaluating. Let us evaluate this function at these 4 values. So maybe I will just take this, copy, and paste it 4 times as we evaluate at -1, at 0, at 2, and at x equals 5. So first, evaluate the function at -1. -1 minus 4, that goes in absolute value. And then we have 3 times the absolute value of -1 minus 2. Well, this is the absolute value of -5, which is +5. And then we have 3 times the absolute value of -3, which is 3. So altogether, you see we have 5 plus 9. This is 14. Now, what about at 0? This is just the absolute value of -4 plus 3 times the absolute value of -2. So this is +4 plus 3 times 2. This is 6 plus 4, which is 10. Now we have 2 more. Evaluate at 2. We have the absolute value of 2 minus 4 plus 3 times the absolute value of 2 minus 2. Well, 2 minus 2 is 0, so we just get 2. Maybe I'll write plus 0. And lastly, at 5, we have the absolute value of 5 minus 4 plus 3 times the absolute value of 5 minus 2. 5 minus 4 is just 1, and the absolute value of 1 is 1. Then we have 3 times the absolute value of +3, so we get 10. So here are 1, 2, 3, 4 function values here. The next example, find all x values satisfying the absolute value of 2x minus 3 is 7. Well, there's really 2 possibilities. Either what's inside of the absolute value is equal to +7, in which case the absolute value of 2x minus 3 would be 7, as we're looking for. But the other possibility is what's inside the absolute value is -7. And here also, the absolute value of -7 is 7. And so we have 2 different things to solve. Here I get 2x is 7 plus 3. I get x equals 5. And over here, I get 2x is, well, minus 7 plus 3. I just add 3 to both sides, which is -4. And so I get x equals -2. So I have two solutions here. One is x equals 5 and one is x equals -2. Now you can check if you just evaluate this at 5, we would have 10 minus 3, which is 7 on the inside of the absolute value. That works. And then evaluate this here. We would have -4 minus 3 on the inside, which is -7. And when we take its absolute value, +7. So we could check both of those answers. Well, let's do the next one. It's very similar. We will have two possibilities. So maybe a first step, you see, what we want is we can just add 2 to both sides. So we want the absolute value of 1/4 x minus 5 to be 2. And just as above, there's two possibilities. Either 1/4 x minus 5 is +2, or 1/4 x minus 5 is -2. So I can just, let's see, the first one I can add 5. I get a 4th x is 2 plus 5, which is 7. And we conclude x is 7 times 4, which is 28. So this is my first possibility. And my other, well, it's similar. We add 5 to both sides. I get 1/4 x is -2 plus 5, which is 3. Now multiply by 4. I get x equals 12. So once again, we had two different solutions. We had to treat the case when what was inside the absolute value was either positive or negative. Okay, wonderful. Here we are given a function. You see, it is a composed function where we have an inside function, x squared minus 4, and then we have an absolute value. We want to do two things. First, we want to write this as a piecewise defined function. And we see a graph here in purple. But the second thing is find all x values satisfying f of x equals 5. So we need to think some. First is you have to think when is what's inside 0. Because if we go back, I'll just do absolute value of x. This function alone, as we saw on the first slide, it's x if x is greater than or equal to 0, and it's minus x if x is less than 0. And so now I need to think about this, but with this inside function being either greater than or equal to 0 or less than 0. So in order to do that, I need to set this to 0 first. And when I do, well, you could factor or just set x squared to be 4, and we get x is 2 and -2. So this is the places where what's inside the absolute value is 0. In fact, we can see it on our graph. Here's 2 and here's -2. Great. Well, now one way to think about this, and I'll do this later in some problems, is we can do a number line. So here's -2, here's 2, and I know this function is 0 here and here. See, it's 0 here, it's 0 here. So to figure out where it's positive, we can just test a point inside. Let's say 0. Is 0 squared minus 4 positive or negative? It's negative, so I can put a minus here. Now pick some, so I tested 0 in my mind, and now we can pick something out here, and we can pick something out here. Say we test 3, and say we test -3. At x equals 3, 3 squared minus 4 is 9 minus 4. This is positive. And at x equals -3, we have the same thing, 9 minus 4, which is positive. Now, using this number line, we can write down our function as a piecewise defined function. First of all, I will go interval by interval because you see I have 3 different intervals here. So let's do x bigger than or equal to 2. For x bigger than or equal to 2, x squared minus 4 is greater than or equal to 0. That's what we figured out. And so the absolute value of it is the function itself. I will say if. Well, if you are between minus 2 and 2, this is where x squared minus 4 is negative. And so my f of x is negative x squared minus 4. Of course, you could distribute the minus sign across the parentheses. This is 4 minus x squared, but I will just leave it like this. It's fine. And the last one, if x is less than or equal to negative 2, again, on this interval, x squared minus 4 is positive, and so the absolute value is x squared minus 4. This is a great example, and this kind of thing you will do definitely in calculus, so it's a good thing to practice right now. Well, letter B, find all x values, satisfying f of x equals 5. We could look at the graph. In fact, let me just add a line to the graph. There's y equals 5. Just looking at the graph, I am expecting 2 answers here. I am expecting 2 answers here and here. And eyeballing it, it looks like 3 and minus 3, but I'm going to do this algebraically without just reading points off of the graph, because this is a very nice exercise working with absolute values. So if you think about the exercises we did on the last page, I really have 2 possibilities. One is x squared minus 4 is equal to 5. And the other one is x squared minus 4 equals negative 5. So let's solve the one on the left first. I have 2 choices here. I can either subtract 5 from both sides and factor, but I will just add 4 to both sides. And I get x squared is 9. This gives me x is 3 and minus 3. So this is what we're seeing here in our graph. But it looks like by looking at this other option that we're going to have more points that I don't see on the graph. So let's work with this one. Well, if we add 4, we get x squared is minus 5 plus 4, which is negative 1. And you can see the issue here. What I need is x squared is negative 1. We have no real solutions to this. And so our only answers are here. X is 3 and minus 3. This next example is great. We are going to find the x and y intercepts of the graph for this function. And we've practiced x and y intercepts some of the exercises, but this is, well, it's another example, and it's going to be a lot of fun. Let's do the y-intercept first, because this is typically easier. To get this, we just evaluate the function at 0. This will be the absolute value of negative 9, which is 9. So as a point on the graph, we get 0, 9. This is our y-intercept. You notice there's only 1. You can never have more than one y-intercept, not for a function, because that would fail the vertical line test. But x-intercept is different. You can have multiple x-intercepts for a function. In fact, we will see more than one in this example. How we do this, we set the y equal to 0, or set the function equal to 0 and solve for x. So we set 0 to be the absolute value of x squared plus 8x minus 9, and then we want to solve. Well, our first step here, note that an absolute value is 0 only when what's on the inside is 0. So I can just say what I want is x squared plus 8x minus 9 to be 0. And here I'm going to need to factor. This is a wonderful exercise. Factoring is one of those skills. Factoring a quadratic is one of those skills that you want to be as good as you can at. when you take calculus. I see the -9. That means I'm going to have a minus and I'm going to have a plus. And then I need two numbers that multiply to -9 and add to +8. Let's do 9 and -1 like this, right? Multiply, we get -9. Add them, we get 9 minus 1, which is 8. And so this works. But this tells me my answer here, my x's. Well, when I set x minus 1 to 0, I get 1. And when I set x plus 9 to 0, I get -9. So now let's write them as ordered pairs. I have 1, 0, and I also have -9, 0. These are both my x-intercepts. I have two of them. Now, just a remark, because I'm about to solve some inequalities, but this is important to think about. The absolute value of x, it measures the distance from this value x to 0 along a number line. And if you have two different numbers, x and y, the absolute value of x minus y, it gives the distance between x and y. So here's my first inequality. We're going to do a few of them. And what this is saying is you want to find all x values that are within 8 of the number 3. That's what that says in words. So you have two options of how to solve this. The first is use a number line. There is 3. Now you move in both directions by 8. And that would mean that this and this, well, this one would be 3 plus 8, which is 11. Maybe I'll write that underneath. This is 3 plus 8. And then we take 3 minus 8. We get -5. But this is -5. And we want less than or equal to. So this will be closed. This would include both endpoints because of that less than or equal to. So now we can just write this. Our answer is the closed interval from -5 to 11. And I really thought about distance here. Another way we can solve an inequality involving absolute values. So here C is some positive number. If you have absolute value of y less than C, maybe I will highlight this. This is equivalent to number y being between -c and C. On the other hand, if you have absolute value of y bigger than C, this is equivalent to either y itself bigger than C or y less than -c. Let's go back and solve this inequality that we already solved using a number line, but using properties. And then we will do one more. So here I have the same inequality, absolute value of x minus 3 less than or equal to 8. If we use this yellow highlighted property, this means that x minus 3 is less than or equal to 8 and bigger than or equal to -8. Now, let's just add 3 to everything that we see. We would have -8 plus 3 less than or equal to x less than or equal to 8 plus 3. And this is -5 less than or equal to x less than or equal to 11. I can write this in interval notation. In fact, you will realize, hopefully, it's the same answer that we had before. -5 to 11, closed interval. Let's do one more. This one I think is easier to use properties than to try and use a number line. So we want to solve absolute value 3x minus 4 greater than 2. There's two possible things here. One is that 3x minus 4 is bigger than 2, or we could also have 3x minus 4 is less than -2. And now we just want to move forward with each one of these and say something about x. If we just add 4 to both sides, we get 3x is bigger than 6. And now divide by 2. We have x is greater than 2. Well, Or let's do the other one. 3x minus 4 could be less than -2. But this is going to be similar in my steps in that I want to first add 4. We get 3x is less than, well, -2 plus 4. You see, this is 2. 3x less than 2. Once again, we can divide by 3. And we get x is less than 2 over 3. Let's write our final answer in interval notation. We see it. It's going to be a union of two intervals. So we have the bottom one is minus infinity to 2/3. This is the x less than 2/3. And then we have union. We have x bigger than 2, which is 2 to infinity. So this is the answer here. This was our absolute value lesson. At this point, you can work the exercises and move on to the exercises video.